to Z equals L. This, of course, are two infinite planes. The electrical conductivity is zero. Infinite. The resistivity is zero. We will control the pressure at the boundaries. The pressure extends uniformly along every field line, and let's just say the pressure is constant, or zero, whatever is easiest to think about. The point is there's no gradient of the pressure. And the magnetic field is uniform. Now let's take this simple configuration and deform it in a rather basic way to give ourselves some topology. When I refer to untidy topologies, that's what we're about to do. The mathematical prescription for winding in interlacing, you hold the field fixed at the lower boundary, and then you displace the foot points, in fact, the fluid throughout, and lace it up. And I drew this little sketch here to indicate the kind of thing that I have in mind, to which I apply the term untidy. It's not a very mathematical term, but it seemed to describe the situation fairly well. Oh, thanks. Let's introduce an incompressible velocity, because I'm treating a fluid, an incompressible fluid here. It's just a simple swirling, no motion in the z direction. This is a two-dimensional displacement, and the function psi is constructed this way: x, y, and kzt, so that the representing the passage of time, which goes fastest up here at the top and slowly down at the bottom. And if you work it out, you'll find that's what it takes to wind in things up here and have them extend down along the field lines all the way through. And just to fix ideas, let's suppose that we have a correlation length in this untidy field here, a correlation length lambda, which is small compared to L. That is to say, there's lots and lots of little interlacing through here. Let's say there are n of them, where n is a large number. They're all independent of each other, and we will use those facts later on in interpreting the magnetic field of the equations. Now, after a time tau, when the field is thoroughly untidy, we will switch off the fluid motions, and then we will clamp the field at the top and at the bottom, and we will then release the fluid in between and let the field itself push the fluid around, seeking the lowest available energy state. We put a little viscosity into the fluid so that there is dissipation, and asymptotically the field will relax to whatever the final equilibrium state is. I want to emphasize that with a field whose foot points are fixed at both ends, there is a stable equilibrium. I'm not going to prove it, it's just an obvious fact. That field is tethered, it can't get away, it can't go on wiggling forever because it's dissipating its energy, moving the viscous fluid around, and so it must eventually settle into a stable equilibrium, the lowest available energy state. And I want to emphasize, too, that the field topology, the untidy field line topology, remains invariant throughout the relaxation process. And eventually, then, this final asymptotic state will be described by the equilibrium equations. And you're all familiar with them. I write them down here. Curl B equals alpha B, the force-free field. And that equation is not like the equations we are used to using. It has mixed characteristics. First of all, let's look at alpha, which I will call the torsion coefficient. Alpha is the ratio of a little line integral of field around any point, or around any small circle, let's say, divided by the flux through that circle. So it's well defined, and it represents the net torsion. Let's go back and take the curl of this equation here. It gives us this equation here. And if you look at it, you see the Laplacian operator, and you recognize that as a quasi-linear elliptic equation. It has two families of complex characteristics. We're not unfamiliar with elliptic equations. However, if you take the divergence of this equation up here, you get b dot grad alpha equals 0. The torsion coefficient is constant along each field line, and you realize then that the field lines are a family of real characteristics, and this equation then has both real and complex characteristics, and that gives it properties unlike the equations with which we usually work. Usually they're purely elliptic or purely hyperbolic. This one is a mixture, and it gives it some peculiar properties. And I keep emphasizing this because sometimes some people feel that the conclusion is not allowed by simple math. Because the equation is elliptic, suppose I start at the lower plate and do an expansion in z. That ought to go some distance at least. And I can compute the derivatives here in terms of the coefficients here, in terms of the field gradient. The derivatives with respect to z are given from curl b equals alpha b by these relations here. And you can see then that if I knew the field at the lower end, z equals 0, I could compute this first coefficient and have a linear extrapolation into the region. And of course I can go back and compute all the second derivatives and repeat it. But the problem is that I don't know the field ahead of time, so I cannot compute these coefficients. And if you think about it a little bit, that's as it should be, because the value of the transverse components, bx and by, depend on how the field is interlaced, the manner in which the field lines depart from the lower plane, z equals 0. So I cannot approach this problem in a way that I might think of doing. And then the question is, where is the information that I need to finish, to go ahead and one way or another solve the equation? I don't have enough information to use that simple expansion scheme. And the answer is that the information is tied up in the topology. The interlacing of the field lines contains the information that determines the final unique solution. Well, that doesn't help very much, because it's one of those things where I can't compute the characteristics, the field lines, along which alpha is constant, until I have solved the problem, and I can't solve the problem until I know alpha, and you see we're running into a difficult situation. I want to go back to an equation on the previous page. Actually, it's 2 pages back. And point out that we were given some warning there and chose not to heed it. This equation here is telling us there's trouble ahead. It says that the torsion coefficient is constant along every field line. And yet I have specified that I will arbitrarily wind the field, individual flux bundles and lines through a succession of arbitrary patterns. First one way, and then another way. And how in the world can the torsion coefficient remain constant along that field line? And that's a necessary condition for equilibrium. So you can see we're headed into some kind of difficulty, but we are undaunted. I look at the curl b equals alpha b, and it's somewhat daunting. So I will dilate the system, stretch the system in the z direction by a large factor, which I call 1 over epsilon, where epsilon is small. And that has the effect, well, it has relatively little effect on the z component, just stretches the field. The x and y transverse components, on the other hand, are expanded and therefore weakened by about that same factor. So it occurs to me to write the field as order epsilon, allow for a correction to bz, which isn't changed very much, and recognize that the torsion coefficient, because everything is stretched out in this direction, will also be small, order epsilon. And of course, because I stretch it, the derivatives of everything with respect to z are small, order epsilon. And I substitute this into curl b equals alpha b. And you get a bunch of equations that look like this. These are the three components of curl b equals alpha b. This is the statement that the divergence of the field is 0. And this is the statement that b dot grad alpha equals 0. And I look up at these equations and I see this is slightly out of focus here. I'll move it back into the center. If you look at this equation, there is b sub z, and the other two terms are order epsilon, which tells me then that bz must also be order epsilon, and that's just telling me that bz is a very small correction to the z component of the field. That makes it second order in epsilon, because here's another epsilon here. And on that basis...
The derivative should go for the epsilon.
Excuse me?
The derivative should go for the epsilon, right? Not necessarily bz itself. Bz can go for the 1.
Well, partial with respect to z is small compared to partial with respect to x and y.
Yes.
Yeah. And we sort of follow our nose through this. The equation for the divergence, the z term drops out, and I have it says that the two-dimensional divergence is 0, so I can write the transverse components in terms of a vector potential in the z direction, call it theta. The third equation in equilibrium then tells you that the torsion coefficient is the Laplacian of theta, and the fifth equation, which was b dot grad alpha equals 0, reduces to this equation here. A replaced with the Laplacian of theta. And, if you look at these, Van Ballinghoe pointed out many years ago that these are exactly the vorticity equations, where you would write two-dimensional vorticity. You'd write the velocity in terms of the stream function. The vorticity is the two-dimensional Laplacian, and the dynamical equation is this thing here, which is exactly the same as that thing there. That says then that the torsion alpha varies along the field in exactly the same way as the vorticity varies along a world line as a function of time. And that equation has been studied at great length. It's studied at great length because it's so hard to grind out solutions. But in any case, it's been studied and one knows the properties of it. And that is that the field evolves in certain definite ways. For instance, the entropy, that is the square of the vorticity, evolves towards smaller scales and so forth as time evolves. Again, no surprise. I mean, that's what you know about turbulent media. And you have an infinite set of solutions at that point. The point is that they all have very special properties. They satisfy the two-dimensional vorticity equation, which has well-known and progressive properties. But then I realized that the winding and interlacing of the field lines that I introduced earlier does not have those simple properties in almost all cases. I mean, clearly, that progressive evolution is a possibility, but it's not the one that I had in mind, and in general it does not occur. So we're beginning to corner ourselves here with some difficulties. We can see that the equilibrium equations do not have solutions for the untidy topology that we would normally wind into the field. But on the other hand, I know that every one of those cases that I have deliberately wound into the field has a stable equilibrium. And I have worked out the equilibrium equation which is incompatible with it. So somewhere there is a contradiction. Well, there are no contradictions in nature. There are contradictions only in the minds of foolish physicists who have made an unjustified assumption, a tacit assumption in this case. And I have assumed that, like all solutions with which I am familiar, the result of solving curl B equals alpha B gives continuous fields. And apparently it does not. Some of the, in fact, almost all of the equilibrium fields have discontinuities in them somewhere. And let's think about what that might mean. And just let me emphasize the predicament in which we find ourselves. Random interlacing of the field lines exists. It's a mechanical operation. I can do it. I know that a stable equilibrium exists because the field lines are tied at both ends, and yet the equilibrium equation cannot accommodate them. And so we think of tangential discontinuities. These are simple enough. Imagine that I have a uniform field. I can take any plane through it and rotate one part of it relative to the other, because of the that's because the well, one would say it's because the field lines represent real characteristics, and you can slide them across any plane, or in fact a lot of any other configuration. And we have then tangential discontinuities, a current sheet, across which the magnitude of the field is uniform, continuous, and so you have pressure balance, and the direction is discontinuous. And this is implied by the fact that we know there is an equilibrium, and this gets us off the hook, because on that discontinuity, neither the field nor curl B or anything else is defined, and in that way we escape the restriction. That's how the system escapes that problem we pointed out earlier, that B dot grad alpha equals 0, which says that the torsion coefficient must be constant along each field line, which is too strong a demand. Let's take a look then at how you might form discontinuities. And I have in mind investigating something like this, where in the field you have one bundle of flux pulled across another. You can see they press against each other here, and let's see what that means. I will use the optical analogy. That states that a potential field, a magnetic field describable by a potential, the field lines follow the same curves as a light ray, a path of light, in a medium with an index of refraction proportional to the magnitude of the field. And so let's say a few words about the optical analogy. First of all, let's define a flux surface. I go out into the field and I draw a curve C anywhere that I choose, in any direction that I like, and the field lines that intersect that particular curve form a surface, not necessarily a plane, in fact generally not a plane, and that's a flux surface. I mean, it's just a common terminology used in describing the fields. And now let's point out that in the field of curl B equals alpha B, the field in that two-dimensional space that we call a flux surface is a potential field. And you say, wait a minute, the curl B is not 0. Well, if in a two-dimensional space, if the field has a curl, the curl is perpendicular to that surface. But the equation for equilibrium says that the curl B is not perpendicular to the field, it is parallel to the field. And so you can see in that two-dimensional space, you do not have a curl. And so the field is expressible as the gradient of a scalar. And remember, this may be in a non-Euclidean space, because the flux surface is generally not a plane. But in any case, we can write the field as the gradient of a scalar. The curl arises then because in the three-dimensional space, because the flux surfaces are twisted relative to each other as you progress, and that gives you the curl B equals alpha B. That gives you a curl in the direction of the field. And if B is expressible as the gradient of the scalar, then the field lines, dxi by ds, have this expression up here. And then if you turn to a wave, e to the I phi, the wave fronts are represented by phi equal a constant. There's some interesting physics here, you know. I've always wondered. In my experience, the transparency always slides away from you, never toward you. And well, this is the ray path in the index of refraction n for this wave here, and you see it's the same equation as I had here, with n replaced by b. And so we can think about an optical ray and an index of refraction b, and the orientation of the field, of course, is not constrained by this. It just says you name 2 points and that are connected by a field line, and in the space between, that field line follows what would be the ray path in an index of refraction b. And now we can use Fermat's principle, we can use the Euler equations, any of the optical. Oh, thank you. It shows the power of money. Well, let's think about Fermat's principle. Simply that the path, the integration of the index of refraction along the path is an extremum, generally a minimum. And let's look at the diagram I have drawn down here. Imagine that there's some place represented by this oval here in which the field strength is slightly above the average. That is to say, something like a couple of flux bundles pulled across each other, compressing the field slightly. And let's think about the field line that goes from C to E. Now the shortest field line would be the straight line across here, right across the maximum, and then straight on out here. But of course it pays the price of experiencing a higher index of refraction in this small region here of width 2w and length 2h. And so the optical path length for that CQE is 2lb plus 2h delta b. That's the price you pay for going over the hump. If that gets to be too large, it is shorter, optically speaking, for the ray path to go around the side, and this way it avoids the larger index of refraction, but of course it's a longer distance. And if you work that out, assuming that w and h are small compared to L, you get 2lb plus bw squared over L. So which is the path that it's going to take? And if the compression of the field there exceeds the amount indicated here, delta b over b is greater than w squared over 2hl, it is shorter, optically speaking, for the ray path to avoid that maximum and go around it. Well, L is large compared to W. Take the simple case that W equals H, and you get this simple criterion here. And you find that if L is very large compared to W, it takes only a very slight increase in the field. And what happens then when you have such a region? Suppose this is the region of increased B, that is delta B is positive here. You can see that there's going to be a hole in the flux surface because all the field lines, these are not field lines here, that's just to show the geometry of the surface. The field lines avoid that, and there you have a gap in the flux surface, in fact, in this slab of flux. And that means the fields on either side, it's hard, well, like on the lower, it could be the field below and the field above, come in contact with each other through that hole in this flux. And in general, they're not parallel. They were separated by a finite distance until they came to this hole. And so they press together and give you a discontinuity. And as nearly as I can see, that is the principal effect. It's the source of the discontinuities, and it just happens automatically. Well, now let's describe very carefully what's going to happen. I start with my imposed untidy topology with all the interlacing. I let it relax, and the Maxwell stresses, the magnetic stresses, immediately begin pushing the fluid around so that it can get into its equilibrium configuration. But the equilibrium configuration involves discontinuities. Well, that means the Maxwell stresses begin to displace the fluid and the field, working towards steeper and steeper field gradients, that is, trying to form a discontinuity so that it can finally be in equilibrium. That's an asymptotic process. It decays exponentially. The divergence from that decays exponentially with time, and the gradient steepens, and not until it finally becomes a true mathematical discontinuity do I have mathematically precise equilibrium. Well, nature prevents us from having to go through that problem because there is some finite resistivity wherever you are. I've said so far, assume it's 0. Now let's get real. And there eventually becomes a point where the slow approach to the discontinuity is offset, or is canceled by the dissipation in the extremely intense field gradients, that is, the extremely intense electric currents. And you have then what is called rapid reconnection, with which I'm sure you're all familiar. And each of these potential, boy, we need almost to put heavier money on this system. It's each of these potential incipient discontinuities then becomes a site for what we commonly call rapid reconnection. The word reconnection is sometimes used without specifying exactly what one has in mind. I should digress for a moment. If I have any field that is not self-similar, when it decays, there will be a reconnection. Remember, you can define a field line by the elements of fluid that it threads through, and unless the system is self-similar, as it relaxes due to resistive decay, the connections between the elements of fluid changes, and that is technically reconnection. In astrophysical circumstances with large magnetic Reynolds numbers, it's not very interesting because usually, long before it has a chance to do much reconnecting, some dynamical effect will have come along and preempted it and changed the whole situation. So it's when you have dynamically driven steepening of the gradients of the field that you really get something that one would call rapid reconnection, and it would be interesting. So let's take a quick look at rapid reconnection. Rapid reconnection occurs when two oppositely directed field components are pressed against each other. I've drawn a sketch here. The fluid from between those two oppositely directed field components is expelled because the pressure is higher here in the center than elsewhere. And in fact, if the pressure is higher by something like v squared over 8 pi, the fluid in between is expelled at about the Alfvén speed, and you end up with a rate of merging due to the resistivity that's the Alfvén speed divided by the, well, it's Lundquist number actually in this case, by the square root of the Lundquist number. If I did nothing to push these two opposite fields together, it would be the Alfvén speed divided by the Lundquist number. Now we're dividing only by the square root of the Lundquist number, which is an enormous enhancement when you have large Lundquist numbers like 10 to the 10, 10 to the 15, and so forth. But it's way short of what nature seems to be able to do. So let's look a little further. I'm just going through the history, really, of the development of this subject. You get, well, this is just a sketch of them, and reminding you of the many things that can happen. Down at the bottom, I've shown the formation of islands due to resistive instabilities. It's been pointed out that if the current density in the region between the two opposite fields becomes too high, you excite plasma turbulence and have anomalous resistivity, which greatly enhances the rate. And perhaps most important of all, and I think I can say most astrophysical settings, the Lundquist number is so large that the thickness of the current layer becomes comparable to or less than the ion cyclotron radius, for instance, and it's no longer legitimate to use MHD. Somehow that obvious fact was very, very slow in being recognized. I, for one, feel foolish for not having noticed it, but fortunately somebody was smart enough to notice it. And that means you have to treat the current layer in terms of plasma kinetics rather than simple Ohm's law or some equivalent law. And Viscamp and Drake studied this, and they concluded several things. I won't try to separate out exactly which each one of them said because they reinforced each other. If you concentrate the dissipation at some particular point in the current sheet, I guess I don't have the right diagram showing here. Well, I can indicate it here. Now I have the sheet palm side up. Here I have pressed the fields together over some broad length that I'm calling lambda, and that you use that scale to compute the appropriate Lundquist number. Many years ago, Petschek made a fundamental observation that you don't have to. The field may not press together over a broad region like this, but only over a very narrow region in the middle. He rationalized this by constructing a situation involving some slow shocks where it was self-consistent. I think that's actually not the way it should happen, but his point is of fundamental importance. And Viscamp and Drake and the experimental work of Yamada and so forth have shown that if you do nothing in particular and just push two fields together, you get this, and you get the reconnection at Alfvén speed divided by the square root of the Lundquist number. But if there is some increased resistivity of one form or another right here in the middle, then the fields will engage only here in the middle, and you get a very much accelerated reconnection. The effective lambda then is only the little distance across this region of enhanced resistivity, and you begin to get rates of reconnection that look like what you see in nature. And as an empirical statement, you find that the rate of reconnection at which fields move toward each other can become somewhere between 10 to the minus 2 and as much as 10 to the minus 1 times the Alfvén speed. That gets to be pretty fast in some of these fields where the Alfvén speed may be 500 kilometers per second. You take a tenth of that, that's 50 kilometers per second, at which these fields can eat into each other. Well, with the results of Biskamp's numerical experiment and Drake's treatment of the kinetic properties of the current layer, it seems that the field is very likely to settle into that rapid Pechek reconnection. And so you have both the what I call rapid reconnection at c over the square root of the Lundquist number, and then what I like to call ultra-fast reconnection, namely some fraction like 0.1 times the Alfvén speed, when you have excited either anomalous resistivity or when the kinetic properties of the plasma give you the enhanced dissipation. So let's go back and have a look at our discontinuities. Let's talk about them a little bit and see what we can conclude. There is no easy way that I know of to determine whether pushing a couple of components together will actually break out into the ultra-fast reconnection, but it evidently does, and is not implausible that it does so. So this innocent question we began with, in which we wondered about the equilibrium of the untidy topology, the first thing it does is try to develop surfaces of discontinuity so that it can escape the restriction that B dot grad alpha equals 0. In the process, you develop rapid reconnection, and in some cases it's going to burst over into ultra-rapid reconnection. And as I say, I can't think of any criterion where you can, where you know the parameters well enough, let's say in the solar corona, to distinguish which ones will and will not. The applications of these spontaneous discontinuities in untidy field topologies, I think, is important in such places as the X-ray corona of the sun. I realize I don't have a picture. I showed a picture the other day of the little X-ray loops. Most of the X-ray emission from the sun comes from little magnetic loops. Either you see the whole loop, or one of the loop starts out and fades out and obviously closes on some larger dimension. And the gas in that loop, well, let me emphasize that there's a whole field here. Let's say a bipolar field. I think I have a sketch of, yeah, something like. I realize this is fairly faint. Well, the bipolar fields look like this, and the interlacing is on a much smaller scale than I've drawn here, because the foot points connect into the surface of the sun, where you have granule scales of typically 500 kilometers, and they're constantly being moved randomly around, and so you would expect the field to have this random twisting and interlacing in it, and it fulfills the properties that we've discussed here. In the present case, I straightened out the curvature, of course, by taking two parallel plates, but the curvature of the overall bipolar field is not really important. And the same thing applies. One would expect these discontinuities to form in the interlacing in these fields. And if I may show you a very crude way of looking at the whole thing, here is a sketch of an idealized bipolar field where only one flux tube is being displaced by the random walk. The others are all standing stock still. After the foot point down here has wandered around through this forest of flux bundles, you can get something like this. And you then have, you can estimate the tangent theta based on how far the foot point has moved and how far it is up to the other end of the bipolar region. And you can ask, how much energy must I put in? Well, the observers say that the dissipation rate that heats this million-degree gas is about 1 watt per square centimeter. It's one of the few fundamental observational facts that's easily expressed in 1 watt per square centimeter. Thought of defining a watt on that basis, but I guess it wouldn't be the way to go. you need to put in 1 watt per square centimeter, and given a field of typically 100 Gauss for this vertical field here and for this flux bundle here, you need to move, and assuming the foot point is kicked around at, let's say, 0.5 kilometer per second by the granule motions, you'll find that the field inclination of about 10 degrees means that the work being done down here on the flux bundle, as you continually wind it through the forested field, is about 1 watt per square centimeter, and 10 degrees is a very modest amount. If you look at a time sequence of the sun, you see these little filaments, the little striations lighting up and then fading away, and right next to it another one will light up and fade away, and I assume that's because the reconnection, which has been percolating along at the rapid reconnection rate, is occasionally pushed up to the ultra-rapid reconnection rate, whereupon you release a lot of energy, and the plasma, the temperature comes very high, and plasma expands upward from the chromosphere. That's the view, in any case, of what seems to be happening. And the individual flares that occur in the flux bundle are very small. I've called them nanoflares, and some of the observers say, well, nano and pico flares. You're getting down into the 10 to the 23, 10 to the 22, 10 to the 21 ergs in a total flare. And I think, therefore, it has application to the sun. Well, I've probably talked about too many things this morning, but I would like to leave with you a thought about the unusual properties of curl V equals alpha B, which is traceable to the fact that it has mixed characteristics and has some properties that we're not normally used to. And, well, thank you for your attention.
Thank you for this wonderful talk. I think we have 15 minutes for questions and remarks. So who would like to start?
This obviously this system it is involved in various random motions. There were ideas that turbulence can significantly accelerate reconnections just by bringing multi-clients together at small scales. Do you think it can be important here, or this what is called turbulent reconnection? So accelerating the connection by adding turbulence.
Well, I think this is probably the most effective mechanism I know of. As you say, turbulence is continually massaging the fields and pushing them together and so forth. But what we need in the corona, where the resistivity is extremely low, is something that is systematic, monotonic, and that the field gradient, or the thickness of the current sheet, the field gradients simply increase without bound. And they have to get awfully thin before you begin to get much dissipation. So I think just turbulence alone would not be sufficient. Yeah, I thought about that and other games one could play until I came across this effect. And I think up in the corona itself, I think that this is the mechanism that dominates. There are some observations that suggest that the heating is intermittent. This is what we're getting here. I've got some references here, and we can talk about them. If you look at the X-rays emitted by one of these X-ray emitting loops, you find that you cannot make sense of the ratios of line intensities and so forth without assuming that it is transient heating. That is, if you just say, well, there's an ion temperature and there's an electron temperature, how can I, and certain abundances of heavy elements, how can I balance this and construct this to give me a spectrum like the one I observed? And the answer is, what the experts say you can't. You have to assume that each point is hit suddenly with an injection of energy, and then it cools for the next 10 or 15 minutes. That's the kind of time scale we're talking about. And then you superimpose a lot of these, and you can begin to duplicate the observations. Other people say, well, we better check this out some more, and I'm quite happy to see that they're doing that. So, well, let's see. Tatsukawa and Tsuneta and Japan have analyzed the fluctuations in the individual pixels of Yoko, the Japanese X-ray satellite, and they find fluctuations above and beyond the thermal in the instrument that you would expect, and attribute this to very tiny flares on the sun. That's why I mentioned pico flares instead of nanoflares. The reference point is a full-size flare at 10 to the 32 ergs, so you can scale it down. Nanoflare would be 10 to the 23, pico would be 10 to the 20. It's a tricky business to look at fluctuations which may be thermal and be quantitative with them, but nonetheless it's a fact, that's what they find. So I think we have a way to go before we can be absolutely sure. There are a lot of claims to heat the X-ray corona of the sun with waves, but they all manage to avoid giving you a specific example that you can check. I think it doesn't work. I've tried to fit it with waves. That's the way I used to do it, and you just finally give up. You need waves of high frequency. Well, the main source of power lies in the granules, which have a period characteristic time of 300 seconds, and that's a wave with that period and an Alfvén speed of 2,000 kilometers per second. The wavelength is equal to the radius of the sun, but we're talking about little loops like so. So this seems to be the one candidate. If this works for the sun, it is then the cause of the X-ray emission of most stars. That is to say, most stars emit X-rays, and most stars are the later type stars like the sun. So this would seem to be the major source of X-rays, the most common source of X-rays. There are other stars where I don't think it works. And I should add that this does not work for heating the part of the corona that is open and expanding to produce the solar wind. Because one end of the field is free there, and you start winding in things here, and it just propagates out as Alfvén waves and escapes. So, well, that's the way the situation looks to me at the present time.
A question I wanted to ask a few minutes ago, which you have already half answered.
Okay.
I mean, I personally started nearly 50 years ago. My scientific investigation was this very problem of the heating of the solar corona, and I'd be curious to know how your own views have changed over the last half century or past half century.
Well, I can give you a quick rundown. It was noted long ago that by Bierman, and I've forgotten all who wrote papers on this, Alfvén and others, that you heat the solar corona by doing mechanical work. If you want to do mechanical work, you're not encumbered by thermodynamic restrictions and so forth. And so the question was to identify that work, and people talk vaguely about waves. And the open corona that gives the solar wind, I think, is heated by waves, and it's evident that you have quite a spectrum of frequencies, because the heating in some days is very relatively close to the sun, and other times extends well out into interplanetary space. For instance, at the orbit of Earth, there's lots of measurements of the thermal anisotropy in the solar wind. And the wind is not expanding radially once it gets a little away from the sun, so it's mostly transverse expansion. So you'd expect the transverse temperature to be very small compared to the parallel or radial temperature. And it is that way most of the time, but it's not as much smaller as you might think, as you would expect from just adiabatic conditions. So there must be a fair amount of ion wave acceleration to boost the transverse components. Then there's sometimes when the transverse temperature exceeds the radial temperature, which means there must be very strong acceleration all the way out, I say all the way, a large fraction of an astronomical unit out from the sun. And then for the little coronal loops, such as I'm talking about here, I think it's the local heating due to this effect of the spontaneous discontinuities. There are probably plasma waves emitted from flares also. One must never be exclusive of other things. One simply speaks of the principal heat input. The suggestion that the tiny microflaring that you see in the photosphere is the main source of heat for the solar wind was suggested by Shadia Habal and Ruth Esser, and there's been quite a bit of controversy about it, but it seems that there's plenty of energy in these little microflares, and they would emit a lot of stuff, Alfvén waves at relatively low frequencies, a lot of plasma waves. So I think we're in a much better shape now to say we have plausible reasons for heating the corona, but we certainly are not in a position to be quantitative about it or spell anything out in detail.
But would you consider that the lack of basic consensus is reflecting the lack of certain crucial data that we could perhaps get from suitable missions, or what's your feeling there?
Well, my guess is that the new Solar Probe Plus mission, which, if it ever goes, is supposed to go in 2016, will look for plasma noise in as far as 10 solar radii. You need, most of the time, you need to get pretty close to the sun, I think, to see any action. And that, of course, is just the heating of the plasma that becomes the solar wind. It still leaves the X-ray emission which comes only from very close to the sun. That's another question. And apart from what's already been done in fitting the theoretical spectrum of the X-rays to the observed spectra, which indicates transient heating, I offhand don't know what else to do. I think one has no alternative but to assume it's something along that order. I am particularly annoyed with all the number of papers that are written where they express wonderful ideas and then never put in any numbers to see if it really works. And maybe I'm just too pessimistic, but when I put in the numbers, it doesn't work. So it'll be a while for sure. The X-ray astronomer types seem to have no interest in the source of the X-rays. They simply note that almost all stars emit X-rays, and okay, that's interesting to know, but they don't seem to pursue it. They'd have to look at the sun, which of course is anathema. You observe only at night when you're an astronomer. Well, I don't know how it will disentangle this thing any more than it is right now. And I don't know whether Solar Probe Plus is ever going to go, with considering the budget problems it has.
To what extent is there a connection between untidy fields and the helical magnetic fields?
And tidy fields, you might say?
Untidy fields and helical magnetic fields.
Oh.
Magnetic helicity entered in the sense that
if I have,
the
problem is the variation of the winding pattern along the field. And if you have a nice helical field, offhand I don't see any problem. It's when you start playing games, I have a couple of patterns here, and then I get tired of that, and then I have them wind in some other way. That's when B dot grad alpha is no longer 0, and then I must have discontinuities for equilibrium.
But you could envisage a situation where the field has 0 helicity by simply cancelling contributions to the linkage.
Yeah.
Okay, so therefore the field is still untidy, but the helicity is 0, and this might make a difference in the relaxation.
I wouldn't be surprised. I'm unable to make any statements beyond the qualitative statements that I've made here. I've fooled around with writhe and twist and everything else, and it never gets, I don't get anywhere with it. So if anybody has an idea, feel free to, delighted to have you develop it.
But it's still unclear question whether the helicity is conserved in the connections, right?
Yeah. I have carefully avoided saying anything about it for that reason, yes. Yeah.
We try to address it, but the problem is boils down to this internal helicity of a magnetic tube, which is not unmeasurable in any numerical model, for example.
Yeah.
So you must assume that it's conserved, or you must assume that it's not conserved. You are free to do whatever you want.
Yeah.
Absolutely horrible situation.
Why should it not be conserved?
Why should it be conserved? It's a reconnection process. We are losing magnetic energy, converting into heat. So it is a dissipated process. So we should keep our eyes open.
Yeah, but the rate of helicity dissipation is less than the rate of energy dissipation.
It still can be finite. Less, but less than zero. Who knows?
But it scales with fewer derivatives. And so therefore, in the limit of very large Reynolds numbers, this begins to make a difference, as we have seen in many cases, which Berger demonstrated this is for the time-dependent case. So analytically. So I don't think there's anybody, I mean, does anybody know of anybody who's saying it's not conserved? Magnetic helicity and reconnection?
But even if I'm alone, I will maintain my point, you know. Okay. So majority doesn't win here. Because it is a dissipation process. And we should keep our eyes open, because the situation is an assumption. You cannot measure it even in the best numerical simulations, because there is always this internal space of magnetic line, which you cannot measure in any simulation, because it's internal, it's within a line.
I've spent some time trying to see how to couple helicity into this problem. I mean, it sounds perfectly straightforward. We talk about the torsion in the field as the current helicity, but I've never been able to work out anything quantitative. So if anybody can do that, I think it would be a big leap forward.
Okay, I think we have to move on. Let's thank the speaker again. Talk by parker+yokoi about turbulent cross-helicity effects and its generation.
Okay, good morning. So today I'd like to talk about the cross-helicity effect. And my outline of my talk is something like this. So I think most of you are not so familiar with this type of cross-helicity argument. Applied to dynamo effects. So I will spend some time to explain what it is. And finally, I will talk about how cross-helicity can be generated in turbulence field. But let me start with some personal remarks. And I belong to the Institute of Industrial Science of the University of Tokyo. This is our present building. And we moved this place about 10 years ago. And before that, our institute is something like this. And it used to be a barrack of Japanese army. Okay? But in 1996, two researchers visited us. So that's Karl-Heinz and Paul. And this is me, if you don't recognize. And the person is Akira Yoshizawa. who first calculated this effect in 1990. So at the time we used almost one afternoon to discuss intensively this effect, cross-LST effect. And yeah, all are very young. Anyway, it was 15 years ago. And also, yeah, in the same year, I met another researcher. But unfortunately, I have no picture with him, but I have some note from him. This is that. So this is from Gene Parker. And I met him, and if I'm not wrong, I met him at the city Nagoya and discussed the cross-LST effect very much. And he, at the time, anyway, he encouraged me to consider the physical interpretation of such effect. At the time, first, Akira Yoshida calculated this effect. He and also I did not notice the importance, physical importance of this effect. Just calculate it. And after this encounter with greatest, and I studied with, developed the concept and also consider the physical meaning, physical understanding. So part of my talk is really, how to say, inspired by this discussion with such great researchers. Okay. And personally, another reason why I participated in this meeting is that, this is the top page of conference web page, and you see this figure. I don't know exactly where probably Axel took this figure, but I guess I wrote a topical review. Oh, sorry. Oops. And I don't know, so I cannot show the evidence. But anyway, I wrote a topical review on PPCF, plasma physics and controlled fusion. So in that review, it is I who drew this figure, I think. Anyway, okay. So I have thought I have a proper right to attend this meeting. So, but unfortunately, I couldn't show. I wonder. I know. So anyway, this is just for explanation of notation. So in my talk, I consider cross-helicity density. Basically, the prime quantity is fluctuation and capital quantity is mean field. Okay, so as you know, helicity has several cross-helicity has several properties, but today I just focus on this invariant and also some pseudo-scalarness. And but as was just discussed, the conserved nature of cross-helicity is not so important for me. Conservativeness itself is not important. Of course, cross-helicity is self-dissipate in real turbulent situation. So, but what I'd like to stress is, due to such conservative properties, we can draw a very simple equation for turbulent density counterpart. So this is only the energy in hydrodynamic case. But you see the mean flow energy is written like this. So mean flow gets energy from pressure gradient. Then mean flow energy has this term coupled with mean field shear coupled with radial stress. And turbulent energy can be expressed exactly like this. This is only incompressible case, but as you see, the production of turbulence coming from the inhomogeneity of large scale coupled with Reynolds stress is directly coming from the drain of the mean field. So, of course, in some cases we may have inverse cascade anyway, but due to the conservative nature of energy in hydrodynamics, we have a very clear equation for this. So each term has clear meaning. So the same is the case to the cross helicity in the magnet hydrodynamics, even in compressive case. And this is the equation for turbulent cross helicity in compressive case. So we have this type of cross helicity production term, which is mean magnetic field strain coupled with Reynolds and Maxwell stress, and also electromotive force coupled with large scale vorticity, and also some other very important terms, and also energy, turbulent inhomogeneity along the magnetic field. This is very important. Anyway, so another very important of cross helicity is pseudoscalar. So as all of you know, pseudoscalar can be a measure for the breakage of mirror symmetry. And this is a direct numerical simulation of large-scale spherical shear and by Ladostin Smith. And in the case of dipole-like magnetic field, we have a special distribution of anti-symmetric special distribution of kinetic helicity and also cross helicity. So let me proceed to the facts. Cross helicity good for. So, roughly speaking, cross helicity effect can be divided in the magnetic field generation, possible magnetic field generation, and also turbulent transport suppression. Okay, so in the case of magnetic field generation, if we consider mean induction equation, so turbulent electromotive force can be expressed in the framework of ours, something like this. So in addition to the usual alpha and turbulent magnetic diffusivity effect, if we have a large scale vorticity coupled with gamma is cross helicity. So if we have alpha effect and cross helicity effect, we may have some balancing effect to the enhanced resistivity due to turbulence. That's very important. So if primary effect of turbulence is enhancing the transport, just you can see. But if we have some additional symmetric breakage, then we may have helicity or cross helicity. In such a case, we have this type of contribution. So this enhanced resistivity can be balanced or sometimes overwhelmed by this effect. That's very important. And I have to skip detail of how to derive the expression of this turbulent electromotive force here. But this is a theoretical result. So alpha and beta and gamma. For the simplicity of explanation, I confined myself to only isotropic expression for this. But anyway, so alpha and beta and gamma is expressed. G is green function of turbulence field. So for example, alpha can be expressed kinetic helicity spectrum minus kinetic helicity spectrum plus current helicity spectrum multiplied by green function of turbulence and integral. So of course we have non-local and spatially and temporary non-local effect. That's a matter of course. Anyway. So So gamma itself it can be expressed using cross-helicity spectrum coupled with Green function. Okay, but this expression is too heavy for real application anyway. So, but we can there are some very simple derivation using the equation itself, and this is induction equation, and Guzai park is displacement of something like this. Anyway, so in the case of if in the presence of large-scale magnetic field, and if we assume a positive kinetic helicity in turbulence field, then we have by assumption we have this type of alignment in statistical mean, only statistical mean. Each realization is randomly, but statistically we have this. Then we have this type of contribution. So displacement, if displacement has some inhomogeneity along the magnetic field line. So if in the case we have cross-helicity, we have displacement is something like this. So we have this effect. So in this direction. So the consequence that contribution of this situation is that if we consider U prime cross delta B prime, we always have a negative contribution to this direction. So the result is that if we have a positive cross helicity, we have electromotive force contribution anti-parallel to large scale B. I think this is part of the essence of target kinetic helicity effect. And also, as Fouquet showed in her numerical explanation, and also Uriel showed. So if we have current helicity, positive current helicity in turbulent field, and if we consider, for example, we can consider fluctuating Lorentz force. Then we have a contribution from delta U prime cross B prime in this direction. So this shows if we have positive current helicity in turbulent field, then coupled with large scale magnetic field, then we have a parallel contribution to B of electromotive force. So this shows this effect and this effect will have to say counter react. So anyway, so this type of argument can be done for turbulent magnetic diffusivity, and also main topics is cross helicity. If we have fluctuating field in the large scale vorticity, then this is the assumption of if we have a positive cross helicity in turbulence field. This is only assumption. Then we have by assumption alignment of U prime and B prime in statistical meaning. Then we have fluid element will be subject to the Coriolis-like force due to this large scale vorticity. So it will induce to this direction, delta U prime. So if we consider delta U prime cross B prime, then contribution to electromotive force is parallel to large scale vorticity. So the point is that the effect of cross helicity is coming from correlation between U prime and B prime. That's cross helicity, and also due to Coriolis force. So that's the local angular momentum conservation for this fluid element. So anyway, the consequence is that if we have positive cross helicity in turbulent field, then we have a contribution to parallel to large scale vorticity. That's I think the physical interpretation of this effect. So anyway, we have additionally this type of term in the presence of cross helicity in turbulence and also large scale vorticity to the electromotive force expression. So anyway, I'd like to mention why the cross helicity effect have been missing. So First of all, I'd like to stress this point. So, in many literatures, large-scale large-scale velocity is omitted in very early, at the early stage of derivation. So, because of the Galilean invariance of fluid equation. So, cross helicity will never appear. And also, another argument is that electromotive force is written, defined by this. So, cross helicity is a cosine of U and V. So, in the case of large electromotive force, we may have a small cross helicity. So, cross helicity effect is not relevant to the case of this. This is another argument. And the other is that so rigid rotation itself is never contributed to magnetic field. And also another substantial reason is that the vanishing of cross helicity. So no large amount of cross helicity has been observed in the turbulence. That's a reason. But as I show it, as I will show, so if we neglect mean velocity at all, we also discard the possibility of large-scale vorticity and also large-scale strain motion. So what we can discard is only the translation motion. So it should be very carefully treated. So we retain large scale U in equation of motion anyway. And also, my point is that so electromotive force is expressed with a combination of turbulent diffusivity and other effect. So the point is that each effect can be very big, but in case of balancing, this quantity can be very small. So the point is that turbulent magnetic diffusivity can be balanced by these pseudo-scalars. So my point is that relationship between alpha or gamma and turbulent electromotive force is considered in combination with this effect. This is the primary effect of turbulence. If we have turbulence in turbulence, then we always have this effect. Basically, always have this effect. So the balance is very important. That's it. And also, if we have rigid rotation, so it actually changes the property of turbulence. And and the final point is related to the second half of my talk. So this is how I will check how and how much cross helicity can be generated in turbulence. Okay, so magnetic flux threading is very interesting, but I will skip this subject. And so we have a contribution of three different terms, and if we only consider the balancing of these two terms, then we have this helicity or alpha effect. So basic balance is from alpha and beta, so B and J is aligned something like this. This is a typical situation of helicity dynamo, alpha dynamo. And another limiting case is if we neglect the alpha effect, then we have a balancing, main balancing something, this one and this one. So in such a case, current, large-scale electric current and vorticity align. So this is the case. So we can easily expect. So in such a case, we may have alignment of B, large scale B and U. Okay. So then we consider basic property of cross-eliciting dynamo. So we dare to neglect the alpha effect, only consider this limit case. Then substitute this into this, and then if we consider stationary state, then we have an equation like this. And also, we consider very strong turbulence case. So compared to this beta effect, eta is at first stage can be neglected. So we have this type, which has we found this is a special solution for this state. Okay, if we have alignment of B and U with a coupling constant of gamma over beta, then in the case, of course, with some assumption or approximation, this term can be neglected because of alignment. Of course, this quantity is turbulent quantity, so it does have spatial dependence. So, but anyway, as a first approximation, so we can neglect. Then we have this one and this one also. So this is a special solution in some sense. So so the consequence is that, so if large-scale magnetic field is aligned to large-scale velocity field, and proportional coefficient is gamma over beta, that is cross-helicity normalized by turbulent energy. So if we have a symmetric velocity field with respect to mid-plane of some situation, then we have, due to the spatial distribution of cross-helicity pseudoscalar, it is highly probable we have anti-symmetric distribution of magnetic field as a consequence of this solution. So we have this type of. And also, if, as I will show soon, if we consider the production mechanism of cross-helicity, as I will show soon, we have this type of production mechanism of cross-helicity itself. So if we have, as I showed, if we have energy inhomogeneity, K is energy inhomogeneity along the large-scale magnetic field, so depending on the sign of this term, we have a positive or negative generation to cross-helicity. So, if we have this type of mid-plane is very turbulent and turbulent gradient is something like this, and if we have a threatening magnetic field something like this, then we have we can expect positive generation to upper hemisphere or upper half and negative. So the consequence is that we have positive and negative this spatial distribution of cross-helicity due to this production effect. Then if we have large-scale motion, rotational motion, then we have toroidal magnetic field, something like this. So this shows that without resort to any omega effect, 2
minutes.
Only 2 minutes. Okay, so we can consider toroidal magnetic field can be generated. Oh, I was upset. So anyway, so I will skip some modeling. This modeling is turbulence property can be described as one-point quantity. This is very similar to what Stephen Tobias showed yesterday. So anyway, I have to skip. Okay, so I will skip several applications. So I just like to show in the solar dynamo application. Sorry, so I'm not so well organized. So I consider alpha vector as a perturbation. Okay, so this is the mean induction equation, and as for the zeroth order, only consider this time, and perturbatively incorporate this alpha effect. Then see the consequence. So zero-order term gives this type of solution, as I showed already. And due to the effect of alpha effect, so we have this type of large-scale electric current. So this is aligned to you. So this gives this type of contribution. Okay, so please trust me in this. Of course, we use several assumptions, only consider pi velocity or something. But anyway, so the consequence is that, so if we have positive cross helicity in some places, then due to this rotational motion, we have a toroidal magnetic field, P0. And from toroidal magnetic field, due to alpha effect, we can have some V1 field, something like this. But if we consider the production mechanism of cross helicity itself, this generated magnetic field will always contribute to negative production of cross helicity. That's a very important point. So firstly, assumed positive cross helicity will be suppressed and negative cross helicity will be produced. So then we can have periodic reversal, I hope. This is a toy model expressing this term and this term and this term. Then we can estimate the oscillation period of this toy model. This is consistent with. And also, very recently, I collaborated with Valery Pipin using his board, and he calculated without resort to omega effect, any omega effect, using this toroidal and poroidal and cross helicity equation. Then he can reproduce the butterfly diagram. Okay, so I should finish my talk. Anyway, one of my recent work is coming from collaboration with numerical people, and I consider I asked some direct numerical simulation of MHD flow. This is Kolmogorov flow and large-scale magnetic field in force. The result is that, so this is the electromotive force, this is DNS, electromotive force, and the alpha effect is in this case negligible. And gamma, tablet magnetic diffusivity and tablet magnetic balance by main balance of these two terms, this can be explained. Okay, so this is my, sorry.
Thank you very much. Okay, waiting, we have time for one short question.
You showed how dynamos with phospholicity could grow, but also really elaborated, numerically elaborated dynamo models.
Yes. I'm now trying to do that. And also, I had to skip, but using some numerical simulation, mimicking sunspot flow or something, we can estimate how much cross helicity can be. We can estimate the value of cross helicity. And at present, the value itself is very promising to me. So we have 10 to the minus 1 or 10 to the minus 2 cross helicity generation, or something like this. So this is promising.
Okay.
The Atlantis flow is perhaps one example that I know of.
Sorry?
The Atlantis flow is perhaps one example I know of.
Yeah.
Okay, let's think. Let's try again, and all speakers of this